Hi, everybody. Today we'll continue on the material balance or mass balance. We talked about the multiple unit mass balance already last week, but this week we will focus on the material balance based on recycle and burst. Recycle, because we use recycle, mostly we use to recycle some reactant back to the reactor, like this. This is after we have the fresh feed of reactant, and then we mix some reactant that we separate from the separated after reaction. That's after reaction. After reaction, we have some unreacted reactant. Okay, we would like to save the reactant, and we can send the reactant back to the feed. That's like we send back to the feed. That's okay. Before the reactor, we have some mix with the fresh feed. So this is the process for recycle. That's right. Mostly we have several reasons why we use recycle in chemical process. We use recycle for recovery of catalyst because mostly catalyst, we use catalyst to accelerate the chemical reaction. That's right. Catalyst is accelerate the chemical reaction. And also mostly catalyst is very expensive. If it can use again and again, we have to use it again to save the money, to save the cost. For that case, after you react, that's right, reactant react with another reactant, we use the catalyst to accelerate the reaction. After finish the process, first of all, if we can recycle the catalyst to use it again, that's right, for that case, or to dilute a process stream. That's right, we can dilute the process stream. We can send some stream back to the list, back to the phase, something like this, to control some process variable and to circulate the working fluid. The working fluid like the air conditioning or refrigerant in household, something like this. We use the recycle. That's right. We use some recycle. Okay. For example, we use the material energy balance on air conditioning. For this case, we will consider only the material balance. For this case, the first feed contains 4% water vapor by mole. Okay, 4% is maybe 0.04 mole fraction of water vapor. This is to be cooled and dehumidified. Dehumidify means dewater. Dewater to a water content of 1.7 mole percent water. We get the output is 0.017 mole fraction of water because the content of water is 1.7 mole percent or 0.017 mole fraction. For this case, we have only air and water. The phase is 4% water, remaining is 96% dry air. And also the output is 1.7% water, and the balance is 98.3% dry air. That's right, for this case. Okay. A stream of fresh air is combined with a recycled stream of previous dehumidified air and transferred to the cooler. What does it mean? That's right. Some air, that's right. In this air include dry air and water. Some air recycle. Before output, we recycle some air, right, to mix with the fresh feed. Mostly the composition of the recycle should be the same as the product, and also the same is the output from air conditioning or cooler. It's the same composition. And then the blending stream enter the unit. The blending stream enter the air conditioner or cooler is 2.3 mole percent water. That means 2.3 mole percent water or 0.023 mole fraction of water feed to the air conditioner. And remaining dry air is 97.7 mole percent or 0.977% of dry air. Aside from this. Okay. Some in the air conditioner, some of the water in the feed stream is condensed and removed as liquid. That means in conditioner they have some water, liquid water condensed. That's right, water condensed. Okay. For this case, take 100 mole dehumidifier air diverted to the room at basic calculation. What does it mean? Dehumidify air. What does it mean? The air that's like we go to the room with dehumidified water. This means this stream. That's right. This stream is 100 mole based on this because it's a 100 dehumidified air. That's right. This means is that the output, the amount of water is less than the input because we would like to dewater out of the air. Okay. Based on this, okay. For this flow chart, we draw a known variable and then we have to specify unknown. For example, we know 100 mole of total mass is dry air plus water output. And feed, we don't know the amount of feed, which instead of N1 is amount of feed. And also N2 is amount of feed to the air conditioner, which is the mixture of recycle and fresh feed. N3 is the mass of or amount of water condensed. N4 is the mass of stream out of the condenser. And M5 is the amount of stream recycle. Recycle. Okay, we don't know amount, but we know the fraction for this fraction for this. It is a 1 because it's only water. That's right. We denote as dA is dry air, W is water. Okay. The question is calculate the mole of fresh feed. Calculate N1. Mole of water content. Calculate N3. Mole of dehumidified air recycle. Calculate N5. That's right. The first step we have the basis already is 100 mole of dehumidified air. And the second step we draw the flow chart and label all unknown and unknown already. Okay, the third step we have to make the material balance for this case. For this case, if the general equation input minus output plus generation minus consumption equal to accumulation. For this case, we have no reaction. That means no generation, no consumption. And the steady state process, flow in, flow out continuity, there is no accumulation. That means input equal to output. The next step, we have to do the degree of freedom. For this case, it is a multiple unit. We can do degree of freedom is like, for example, is overall. Okay, if we do the overall, what is the unknown? N1, N3. We have two unknown, that's like N1 and N3. We have two balanced species, dry air and water. For that case, the overall degree of freedom is 0. And for this case, we can solve for N1 and N3. N1 and N3. The next step, we will make the balance out the mixing. The mixing, we have N2 and N5 is unknown. That's right. N2 and N5 is unknown. Okay. But after we make the balance overall, we know N1 and N3. N1 is known already, but now we make the mixing point. We have three unknown, N1, N2, and N5. But now we know N1 already from overall balance. And remaining N2 and N5. We have two unknown, two balance equation of dry air and water we can solve for mixing also. 0 degree of freedom. And then we check the cooler of air conditioner. Now N2 we know already. And then you make all mass balance. Balance air conditioner. We have unknown N3 and N4. Two unknown, two balance on dry air and water is 0 degree of freedom. We can solve for N2 and N4. N2 and N4. And then we balance on the split side. We have N4, N5. But for this case, we know N5 already. So we can solve for N4 for that case. But we not necessary to derive for this because we have the question over the N1, N5, N3. And also we can do the balance around the, in the mixture, that's right. We have not 0 degree of freedom, we have 1 degree of freedom. We have unknown is N4 and N5. N4 and 5. But I think this we know N4 already. We can solve N5. But if you know N4, okay, we have two unknown and only one balance. We have only one balance because the same composition in recycle in this thing. We have only one. We have only one balance. Not two, only one, because it's the same composition. It is based on unknown N4, but for unknown N4 we have one and also 0 degree of freedom. For that case, it should be one variable in phi already. That's right. It should be 0. Okay. In the first step, you have to make based on OR balance. Okay. The first step we make OR dry air balance. Okay. OR dry air balance. Dry air input is the fraction of dry air is 0.96 mole dry air per mole total. Multiply N1 is mole total, we get mole dry air. We have one input and two, and also one output. This is that's right. No air in this steam. We have one input, one output. Dry air output is 0.983 mole dry air per mole total. Multiplied by 100 mole total, we get mole dry air. We can solve for N1. That's right. You get to get the N1 mole of dry air feed. And then we make the OR mass balance or mole balance. OR mole balance. Overall, we have one feed, two output. One is N1 total mass or total mole. Output N3 plus 100. That's right. We get N1 equal to N3 plus 100. N1 we know already from the first equation, and then you substitute N1. You can calculate N3 equal to 2.4 mole water condensate. And then the next step, we make the mixing point balance. Mixing point balance be balance on total balance and water balance. You can water balance or dry air balance is up to you. For this case, we make two: is total balance, total mass balance or mole balance, and balance on the water. Okay, for total balance, input we have two, that are N1 plus N5 equal to N2. N1 plus N5 equal to N2. For this case, we do know N1. Unknown is N5 and N2. Okay, we cannot solve for one equation. Okay, we have to. Another one is water balance. That's right. Water balance allow mixing. Water input is 0.04 mole water per mole total. Multiplied by N1, you get mole water. That's right. Equal to 0.017 mole water per mole total. Multiplied N5 mole total. Plus 0.023 mole water per mole total. Multiplied N2. That's right. You get this equation. We have two equations. You know N1 already. Two equations, two unknown, N2 and N5. You can solve simultaneously. You get N2 and N5. That's right. You get N2 and N5. And then you balance around the condenser. You can solve for N4. That's right. For this case, it's not necessary for do that because the question is to find fresh feed. Fresh feed is N1. Mole of water condensed is N3. Mole of dehumidified air is N5. That's right. Mole of dehumidified air recycle is N5. Okay, you get the answer already. You're not necessary to do more. That's right. Okay, the next equation, next example, that for an evaporative crystallization process. The crystallization process, you would like to separate a solid that dissolve in liquid like brine solution or saline solution. In the solution, we have the sugar. We have the salt dissolved in the water, like sea water. That's right, sea water. By we evaporate. How to do that? We evaporate water out of the solution, and then we get crystal of salt. For this case, we would like to the evaporative crystallization to crystallize the potassium chromate K2CrO4 without a crystal form. That's right, the aqueous solution. This salt is shown below. Okay. 4,500 kilogram per hour of solution that is 1/3 potassium chromate. What does it mean? The flow rate, total flow rate, mass flow rate is 45 kilogram per hour of the solution in the feed. This contains 1/3, mean 33.3% potassium chromate. That's right. It's potassium chromate, and another is aqueous solution, mean water and potassium chromate dissolved in water. That It is 33.3% potassium chromate. That the remaining is water is 76.7% water. That's right. Okay. And then joined by a recycled stream contain 34.6. That's right. This recycle, we call recycle is filtrate. That's right, because this out of the filter. The filtrate contain 36.4 potassium chromate solution. That means the water is 63.6. That's right, water. Okay. The combined stream is fed into evaporator. That's right. It's mixed, recycle, and fresh feed to evaporator. Feed to evaporator. The concentrate stream leaving the evaporator contains 49.4 potassium chromate. That means the stream out of the evaporator is 49.4% potassium chromate. That means another is 51.6% water. That's right, 51.6% water. Okay. And then this stream, that's right, this stream is fed into crystallizer in which it cool. That's right, this crystallizer cool reduce the temperature until we get crystal of potassium chromate crystallize out the solution. And then we filter. Okay, for this unit, we combine crystallizer and filter. After the crystal crystallize, right, the solid form of potassium chromate crystallize, and then we filtrate. Filter. It is a filter cake. It is a solid solution. This is a filtrate, mean the solution. That's right. This solution is contain solute is potassium chromate dissolved in water. That's right, in the filtrate. And the product is filter cake. That's right. Filter cake consists of two, it's solid and solution. That's right, solid and solution. Okay. The filter cake contain potassium chromate crystal and a solution that contain 46.4 potassium chromate by mass. This means that we have separate it is solid and solution. In solution contain the 36.4 potassium chromate. That's right, potassium chromate. Okay. The crystal account for 95% of the total mass of the filter cake. That's right. What does it mean? In crystal, it contains 95% of total mass of filter cake. Amount of crystal is 95% of the total mass of this stick. Total mass of this stick. Okay. And the solution passed through the filter also is this in the recycle stream. That means the composition of potassium chromate in solution. That's right. Recycle to the phase feed and also in the filter cake is the same composition. This is 36.4. 36.4. Okay. The first question, calculate the rate of evaporation. This means calculate the water evaporates out of the evaporator. The rate of production of crystalline potassium chromate, rate of crystal potassium chromate, feed rate, the feed rate that the evaporator and the crystallizer must be designed to handle. Feed rate, that's right, to the evaporator and to the crystallizer. Feed rate and this. And the recycle ratio, mass of recycle per mass of phase feed. Mass of recycle per mass of phase feed. We know mass of phase feed already. Okay, the second question, we assume that the filtrate were discarded. What does it mean? We discard the recycle. If there no recycle, okay, calculate the production rate of crystal. And what are the benefits of and cost of the recycle? Okay, the first question we talk about the recycle. The second question we cut the recycle off. That's right. It only discards of the filtrate, not recycle and product. Let's compare that. Okay, the first step, we have to set up the basis. The basis should be the mass flow rate of the phase feed. That's right. We know the phase feed. And we draw the flow chart. That's right. Okay. The next step, the basis is phase feed. And then we draw the flow chart. This is, we know some component already, and then you draw the flow chart. This is component of potassium chromate, and also another one is water. I talked to you already. And this is the composition in the recycle and total mass rate denoted as M6, and the product That's right. It is the composition of potassium chromate and this water. This is in terms of solution. And this is in terms of solid. M4 is made of solid potassium chromate. M5 is made of solution. And M2 is made of water evaporate. M1 is made of mixing between phase fit and recycle. X1 is the mass fraction of potassium chromate. That's right. And 1 minus X1 is the mass fraction of water. Okay. MT is the mass of the product or of the evaporator. And we know like the mass fraction of potassium chromate. Another one is mass fraction of water. Okay. We finished the flow chart already. We label the known variable. We label the unknown variable. That's right. We have 1, 2, 3, 4, 5, 6, 7 unknown. Okay, the next step we have to do the degree of freedom analysis. Okay, we set the basic. Okay, for the overall balance, if we talk about the overall balance, that's right. We have M2 unknown, M4, M5. We have 3 unknown, and we have 2 balance, water and potassium chromate. That's right. 3 unknown, 2 balance equation, and we have 1 relation because we know like M4 is the 95% of M5. That's right. This is a 95% mass of the filter cake is the Kirchhoff. That means it's 95% of M5. That's right. M4 equal to 95% of M5. Okay. This will reduce the unknown already. Okay. We have degree of freedom is 0. You can solve for it. Overall balance. And the next we check the recycle phase fit mixture. If we balance around this, we have 2 input. That's right. We know phase fit M6, M1, X1. We have 3 unknown and only 2 balance equation. It's 0, 1 degree of freedom. For this case, we cannot solve for the mixing. Okay, the next step, we check the evaporator balance. Evaporator balance. That's right. Unknown is M1, X1, M2, M3. That's right. We have 1, 2, 3, 4. 4 unknown. But already, if you balance overall, you know M2. Right? You know M2 have the unknown is M1, X1, M3. 3 unknown. That's right. 3 unknown. Only 2 balance equation. We get 1 degree of freedom. Mostly we have 4, that's right? M1, M2, but M2 we know from the overall balance. Okay, now is 3 unknown. But we have only 2 species balance. That's right. Okay. 1 degree of freedom. That's right. But now you cannot solve for evaporator. You cannot solve for mixing. And next we balance around crystallizer and filter. For crystallizer and filter, we have feed is M3. That's right. It's unknown. M4, M6, M5. Also M5, M4. We know already from the overall balance. But now we have M3 and M6 is unknown. 2 unknown. 2 balance. You can solve that. That's right. Okay. Now in conclusion, the first step, you have 2 balance overall. You know M2, M4, M5. And next you balance on crystallizer. You know M3, M6. Okay. You know M2, 4, 5, 3. And then you can solve for M2. So you can solve for M1 and X1. Because you know M3 from balance around crystallizer, M6. And then you can solve for mixture or at least if you balance mixture, you can solve for M1 and X1 because you know M6 already. Or you can balance around evaporator. You know M3 already, you can solve for M1, X1. That's it. The first step you have to or the second step balance around crystallizer, and the last step you can balance around mixing or evaporator. That's it. Okay, the first step you have to go to the balance equation. The general form like input minus output generation minus consumption equal to accumulation. For this case, no reaction, no generation, no consumption, and no accumulation because it flow in, flow out continuously. That means input equal to output. Okay. The first step, we have to check the relationship between M4 and M5. That's right. We know the crystal is 95% of the total mass in the output. The total mass in the output is M4 plus M5. That's right. M4 plus M5. But M4 is 0.95 M4 plus M5. That's 95%. Okay, we can relation is M5 as a function of M4. Because M4 is the 95% of M4 plus M5. Is it okay? And then you go to balance, overall balance. Overall balance, you have to balance based on potassium chromate. Overall, okay, you should overall. Okay, the feed, we have one feed. The potassium chromate, that's right, in the feed we have 0.33 kilogram potassium per kilogram total multiplied by 4,500 kilogram total per hour. You get 4 rate of chromate. And output, that's right. The output potassium chromate, we have two. In the crystal form is M4 and also in M5. That's right. M4 in M5. Okay. This is 0.364 multiplied by M5 plus M4. That's right. There is no potassium chloride in this stream. It's only water. Okay. We have this. Okay. This is the feed. This is a crystal. It is a solution. That's right. And then you solve for equation 1 and this equation simultaneously because you substitute M5 like this. You can solve M4. And then you substitute M4, you can solve M5. That's right. You know M4 and M5 already. That's right. And then you solve the overall mass balance. Okay, overall feed is 4,500 kilogram per hour equal to M2 plus M4 plus M5. That's right. This is only one feed to output. That's right. 45 kilogram hour plus M2 was equal to M2 plus M4 plus M5. You know M4, M5, you can solve for M2. That's right. Input, output. You know M4, you know M5, you can solve for M2. That's right, you get M2. And then the next step, you have to balance around electrolyzer. Okay. For this case, the first step, we balance around the overall balance, our total mass balance. The total mass balance around the electrolyzer, that's right, M3 equal to M4 plus M5 plus M6. That's right. M3 equal to M4 plus M5 plus M6. You know M4, you know M5. Okay, you have to another equation. That's right. You know M4. You know M5. And then you can relate it M3 as a function of M6. Two unknown one equation, you cannot solve it, and you have to do another balance. For this case, we make water balance around electrolyzer. Water balance, water input is 0.506 kilogram water per kilogram total multiplied by MT equal to output is 0.636 kilogram water per kilogram solution multiplied by M5 plus 0.636 kilogram water per kilogram total multiplied by M6. That's right. You get it. Okay. You know M5 already. That's right. And then you can relate M3 as a function of M6. Equation 2 and 3 is two unknown M3 and M6. Two equations you can solve for M3 and M6 simultaneously. You get M3, you get M6. That's right. Okay. And then you not necessary to do another balance because you can answer the question. That's right. The question is this means the ratio of recycle per phase feed. The ratio of recycle is M6 divided by the phase feed is 4,500. You get 1.26 kilogram recycle per kilogram phase feed. Okay. And then you can solve for M1. That's right. M1. You can solve a mixing point. Mixing point. Total mass balance, the mixing point is M6 plus 45 equal to M1. That's right. You know M6, you can calculate M1 already. You can calculate M1. Okay, then you can check only. Okay, the answer. That's right. The question is, you can answer the question. Rate of evaporation is M2. You know M2 already. That's right. Okay. Rate of production of potassium chloride in the crystalline, you know M4 is the answer. That's right. This is M4. Feed rate that the evaporator and the crystallizer must be decided whether. Okay. Calculate M1 and M3. This is a feed rate to evaporator. This is a feed rate to crystallizer. Okay. This answer already you know, and the recycle ratio you know already. You get the answer already. That's right. And for the second case, if the process is no recycle, for the process is no recycle, you can draw the flow chart like this. You can draw the flow chart like this. There is no recycle. Okay. For now, we have only 1, 2, 3, 4, 5 unknown. 5 unknown. If you make the overall balance, M1, M3, M4, M5, right? 1, 3, 4, 5, but M3 and M4 you can drop only 1 because you know the fraction is 95%. But for this case, you cannot solve for overall, and then you can check the evaporator. For evaporator, we have 2 unknown. 2 balance. Okay, from evaporator, you can solve for M1 and M2. That's right, M1 and M2. And then you solve for crystallizer balance. We have M2, you know already. M3 and M4, you can drop in only 1 unknown. Okay, we have 2 unknown and 2 balance equation. You can solve for M3, M4, M5. After you make the balance, we get M3 is 622 kilogram potassium per hour. This is the crystal product. If you compare between the product from this M4, M4 is 1,570. That is, if we have the recycle, we get more product, about 2 times or 12. Why? That's like 2 times. Okay. And then you can compare M5. M5 is the filtrate. That's right. About 2,000. 2,000. Okay, 2,000 kilogram per hour. Okay, this is you can do that if we drop out the recycle, the product is reduced. That's right, the product is reduced. Okay, look like this. But the cost is also if you drop the recycle. That's right, you drop the recycle, the cost is no include the purchase, the cost what the cost include the purchase and installation cost for recycle piping and pump. That's right. You have to check if you recycle, that's right, and then you compare the cost. You compare between the cost. That's right. If you get the product is higher and then you sell the product, and then you compare with the cost. If you increase the recycle, and then you check the income, something like the profitability. That's right. I cannot confirm that. We have to check the cost before I do decision. That's right. And the next technique that we talk about bypass. The bypass is a fraction of feed to the process unit because before you feed to unit, we have some fraction as bypass to the product. That's right. What some feed is diverted into the product. That's right. We split into fraction. One fraction is to the process and one fraction is to the product. That's right. For this case, by the fraction of the feed that bypass, we can use this to vary the composition of the product. We can use adjust the property of the product for that. For example, like this, we have the orange juice, red feed contain 12% by weight solid. Okay, we draw the flow chart is 12% solid, which means 0.12 fraction. That's 5 kilograms per kilogram total. And the balance is water. That means and 88% is the water is 0.88 kilogram water per kilogram total. Okay. And the concentrate orange juice contain 42% solid, and the balance is water. You would like to get the concentrate of juice is 42% solid, which means 0.42 kilogram solid per kilogram total. That means it's 58% water. We have two components, water and solid. Okay. We use the evaporator or evaporation process to concentrate the juice. That's right. We use the evaporation. Okay, we use the evaporator to concentrate the juice. And also the volatile constitute of the juice escape with water, leaving the concentrate at the fast. Yes. The current process overcome this problem by bypass the evaporator with a fraction of phase. What does it mean? Okay. Because there are some water as I evaporate out of the process, and then if we would like to control the concentration with to specification, we have to some water or some the phase feed bypass to mix with the product to control the composition. For this case, we have some bypass. The bypass the composition is the same phase feed. We have some bypass. Okay. For this case, the juice that enter the evaporator is concentrated to 58% by weight. That's it mean is its composition. That's right. After the evaporator, we get 58% solid, and the other one is 42% water or the fraction like this. Okay, the first question draw the label flow chart. This process that we neglecting the evaporation in the juice. We only the evaporation of water. Okay, we have to prove the balance and degree of freedom, and B calculate the unknown. Okay. And C, most of the volatile ingredients or provide the taste of concentrate are contained in the fresh juice that bypass the evaporator. Okay, you could get more of this ingredient in the final product by evaporation. 90% solid instead of 58. Okay, you could then bypass a greater fraction of the fresh juice and there be obtained a better taste product. Okay, suggest the drawback of it. Okay, the first I will check this again. The first step you have to draw the flow chart. For this case, you draw the flow chart already. For this case, we don't know the mass or mole or mass rate or mole rate. You know only the composition for each phase. Okay, the basis we utilize the mass of phase feed because we know the composition in mass fraction. For this case, we assume at 100 kilogram of phase feed at the basis. That's right. Okay. We denote M1 is the feed to evaporator. That's right. After bypass, M1 is feed to evaporator. M2 is the bypass to mix with product. M3 is water evaporate. M4 is the product out of the evaporator, and M5 is the final product. That's right. We denote the unknown. Okay. And then you make the degree of freedom for overall process. Overall process, we have one input is 100 kilogram. Output is M3 and M5. We have two unknown. Two composition you can balance. That's why it's 0 degree of freedom. 0 degree of freedom. Okay. For the bypass, we have one input, two output, M1 and M2. This is two unknown and two species balance. You can solve for that. Sorry, not. We have only two unknown, but we have only one balance equation. Why is wrong? Because you can see that this is the same composition, same composition, same composition. That we have only one independent equation. So you can balance on water or solid, but only one independent equation. For that case, we have only one degree of freedom. You cannot solve for bypass, and then you can solve for evaporator. M1 unknown, M3, M4. That's right. We have three unknown. You cannot solve for because two balance and one degree of freedom. And then we check the mixing point. The mixing point like this. Unknown is M4, M2, M5. Based on you balance overall, M5 you know from the overall is M4 and M2 is 2 degree of freedom. 0. Two unknown M4 and M2 and 2 balance equation, you can solve for that. That's right. For this case, you know M5 already. That's right. Based on you know M5 from this. That's right. From overall, you know M3, M5, and then you know M3. You have only 2 unknown, and then you get 0 degree of freedom. Okay. In conclusion, that's right. The first step, you have to balance overall. You can solve for M3 and M5, and then you solve for mixing point. You can solve for M2 and M4. That's right. M2 and M4. And then you can balance around by part. You can solve for M1 because M2 you know from this. And then you balance evaporator. That's right. Around evaporator, you know M3, you know M4. That's right. You can solve for M1 and M4 like this. Okay. Okay. For this example, we make the overall balance of solid. Overall solid, we have 1 input and 2 output. The solid is 0.12 multiplied 100. There is no solid in this step, equal to 0.42 M5. That's right. Okay. This balance, you can solve for M5, and then you make overall balance. 100 plus, 100 equal to M3 plus M5. M3 plus M5. You know M5, you can solve M3 for this. Okay. And then your mixing point. Mixing point, if you balance overall balance on mixing point, M4 equal M4 plus M2 equal to M5. That's right. M4 plus M2 equal to M5. M4 plus M2 equal to M5. But you know M5 already. It's two unknown. One equation you cannot solve, and then you use the solid balance. Allow mixing. Allow mixing solid balance. Input is 0.5s multiplied M4 plus 0.12 multiplied M2 equal to 0.42 equal to M5 multiplied M5. That's right. This input equal to output. You know M5 already. Now you unknown is M2 and M4. Two equation. You can solve this. You can get M2 and M4. Okay. And then you balance on bypass. Total mass on bypass. 100 kilogram equal to M1 plus M2. You know M2 from previous, and then you solve for M1. That's right. You know M2 from it. You can solve for M1. Okay, now you can solve all of M1, M2, M3, M4, M5 already. M2, M1, M2, M3, M4, M5. And also bypass fraction. Bypass fraction is fraction divided by phase speed. This. Okay. Over evaporating could degrade the juice. Additional evaporation could be uneconomical. If you add the evaporation, but also degrade the juice because it evaporates better. That's right. Okay. Maybe I'll see you again for next lecture. Thank you for this.